One of those tools that's come along in modern development is a thing called continuous integration. Continuous integration is when you have a set of tests that you want to run to verify that your code still works on all the things that it used to work on, and every time you make a change to the code base, you basically want to run these tests, or you may have it broken up into different phases, but a little change in the database, you run all the database tests, but you don't run all the tests, and when that change gets merged into the production system, at that point you run the entire set of tests for the entire production set of code. So this is basically universal in most modern development environments. There are a bunch of different companies that offer this service in various forms. Good examples of companies offering this is things like Circle CI, which I used when I worked at Thesis. Travis CI, I've also used that one for some other projects of my own. GitLab has its own internal system, and there's also GitHub has GitHub Actions, which is a continuous integration system. Some of them, like GitLab, have the necessary hooks so that when you check something in to your source code repository, you can actually use an outside system for testing. But all of these things allow you to add your own tests. And the basic idea is that if you don't break stuff that is currently there, then when you ship it, it still works. This has produced a tremendous improvement in the quality of software that gets shipped to customers. And it keeps us developers honest that we don't just change something and forget it. We actually have to change things. Usually, when you make new changes, you're doing it in either because you are creating a new feature or you're responding to a defect in something. And you add tests at that point in time that verify that what you're doing is actually going to work. So over time, the set of tests grows and it becomes more complex. Let's take a little detour into what the flavors of tests are. Usually you have unit tests. Unit tests are things that test a specific piece of your code. And the better you do at unit tests, the more things you find, but they are certainly not a begin-all, end-all in the land of testing. Microsoft did a bunch of research on end-user defects and found that unit tests would catch 21%-ish, 22%, right in that number, of end-user defects. So they don't do all the testing we need. When we move past unit tests, we go up to a thing called integration tests. For instance, if I'm building something that has an API, an application programming interface, I want to have a set of integration tests that run against that entire API, which means the API, the database or databases behind it, how this all gets served across web servers. So I've got to integrate all the pieces together, and I have to do tests that work with that entire set. So those are integration tests. Quite often, you may actually run the entire application at that point too. But you may want to chunk it up into pieces because it's easier to test that way. And those are your integration tests. Make for APIs makes a really nice testing tool. You can sit there and run a particular test and another test and another test. And if one of them fails, you can report it back to Make and it can stop at that point, which means you can have a scripting language to collect your tests together at the integration level. And all sorts of command line tools make this just a breeze for integration testing. Regression tests. Usually these are things that you have a customer defect, that you've gone in and fixed a particular thing, and you want to make certain that that thing stays fixed in the future. As long as we build software where we keep fixing things and we have less and less defects, it's improving in quality. So this is how we keep it going in the right direction. Most places have some level of quality assurance tests. That this is where they actually run the application after the end of everything to make certain that they have a set of tests that verify the entire application works together. And those are important too. But in the end, the only way you're ever going to get thorough testing is if you release your product to some sort of a beta group, because inevitably you have users out there that are using your product for things you never ever thought of. And they will take a hammer, and because they've got a hammer, they will use it to twist screws and remove screws and chop wood and all sorts of things you never thought of because they have a hammer. So they do things you won't think of, and they try things you won't think of. So beta test is also an important thing. I didn't list that in there because it's not usually considered. a testing phase, it's a release phase, but that's a critical piece as well. So customers that actually will run it and give you good feedback. If you do all of these things, you usually catch 89% of the defects. So it's not perfect. But in the midst of these things, usually some of all of 1 through 4 can be done as automated tests. Even the front ends can be tested with things like the library Mocha that allows you to do application JavaScript front end testing and make certain that a lot of stuff works without having human interaction. And when you can run thousands or hundreds of thousands of tests, you're more likely to catch all the defects. I use a database once in a while called SQLite. It has 240,000 tests built into its test suite. That's how you can be certain that when you actually run it, it's going to work today, tomorrow, and the next day. So a lot of effort goes into the testing and validating the tests and making certain all the tests still work. Now, all of this testing and continuous integration has actually resulted in applying these techniques of development and testing and metaprogramming to an entire kind of a career called DevOps. DevOps is the combination of building these things for basically being a system administrator and doing it at scale so that you can automate the process of system administration. And you go, why do you need to automate something like system administration? Can't you just install something and run it? Well, yeah, but what happens when it's at scale? Scale is things like, certainly some operations have very large scale, but I worked on a project with a company down in Denver a while back, and it's not particularly considered to be a large company, but at the time it had 27 servers. If you need to reliably deploy something to 27 servers, suddenly you're into the land of DevOps. And it's a combination of development and testing and building things that are scripts to mangle stuff and work with data and deploy stuff and test it before it gets released into a production environment. An awful lot of software breaks at the point where you release it into a production environment, and sometimes catastrophically breaks. So good process and good DevOps is hugely important. Now, what are the most important metaprogramming tools? Absolutely, beyond a shadow of a doubt, the most important metaprogramming tool is compilers. Compilers take a specification for a language and they translate it into some sort of an assembly language. Usually the compiler then turns around and runs an assembler to build the object files and runs things like a linker to link multiple object files together into final executables. They tend to be rather complex because they do all sorts of optimization and work for us. And they are heavily tested, and these days marvelously reliable in terms of what they do. Amazingly good code quality in compilers. And that is your biggest system tool right there. I'd say the second most important thing is databases. Most applications run these days with some sort of a database as a back end. I mean, Gmail uses a database. And all sorts of things that you use have behind them some sort of a database that they're updating. Databases have been around for a while. We can give thanks to IBM and NASA for the Information Management System, which was the first database server system. And they have become more standardized. There are all sorts of things out there like Postgres and MongoDB and Redis and different kinds of databases for special kinds of applications. For instance, Facebook has developed its own database called Cassandra. It's a marvelous thing if you happen to be Facebook. Some other databases are what I would call world-scale databases. Google has a database called Spanner that it uses atomic clocks in its data centers to synchronize. It's actually, the Spanner database is a relational SQL database running on top of another database called Bigtable. And I know that sounds weird, but yes, a database running on a database, but that's what they have built. And it has all sorts of wonderful capabilities, and it is really, really fast and works at scale. Scale in this case being millions of computers running on a single database all at once, and millions of users using that database all at once. If you've seen an ad on the web, and most of us have, then chances are it came through Google, and all of those ads are tracked and all of your clicks are tracked in the Spanner database, a single giant database. So if this is the kind of stuff that just tickles your fancy and you think you can program well, in the fall, I am actually going to do a project-based database class, in which case we're going to take this database called MongoDB, which is a NoSQL non-relational database that has become very popular with a lot of developers. And Google's comment about these NoSQL databases is they're not actually a good productivity tool, because sooner or later you need actual relational data, and you need to be able to keep track of that data and make certain the data is right, and you also need this thing called ACID compliance, so that the concurrency is managed by the database, not by users, because it's really complicated to get concurrency to work. And it is much better to let a single system get it right once than it is a whole bunch of applications get it right or wrong, and mostly wrong multiple times. So we are going to implement in that class a MongoDB killer. And the MongoDB killer is going to be take the exact syntax of MongoDB and build a new front end for it and a new back end, basically replace the database, but replace it with one that will either run on Postgres as a back end for people doing development or small systems, and run on Google Spanner for at scale. So it'll run on both. And that will be a fun project for a semester project. We'll have some teams and build this thing and actually get it to work. And that's the kind of a database project you do. That, instead of building this, we will actually take their open source and we will scrape pieces out of the MongoDB, like the syntax for their language, and we'll build it at scale. And my suspicion, since I've already done some timing tests on this, is that Postgres will run circles around Mongo, and when you take it to something like Spanner on a single computer won't run circles around Mongo, but with 20 computers running in parallel, I bet I can build a Mongo emulator that is way, way faster than Mongo. And all I've done is I've taken their system and I've replaced the back end with a different system, which is a common kind of optimization for an awful lot of computer architecture. Okay, next time is our last lecture on stuff that we're actually going to cover in terms of computer architecture. We're going to take a little bit of a look at a compiler and see how it works and what it does, so that you've got some idea of what's inside a compiler. And then we are going to move on to our last little subjects on how to use computers at the command line. And then Friday we will have a review, and I will put out the final as soon as from probably noon Friday. The final will be available to you folks. It's a take-home, just multiple choice, and all homework has to be done by Friday, because I cannot make the system at the university work otherwise. I may be able to squeeze in a little bit of an exception if you email me something after Friday, but basically everything has to be done by Friday except the final. I hope you guys, I truly appreciate all the work that's gone into this class, especially under the circumstances this semester, and I just think everyone has done an awesome job.